Good morning. My name is Glenn Winters. I'm the Chief Geophysicist of Fasken Oil Ranch in Midland, Texas. We're a family-owned company. We drill about 150 wells per year, mostly in the Permian Basin, but we're also in the Eagle Ford, and we've drilled wells out in Nevada. I've been in the business for over 30 years. I started off with Texaco, and over those years, I've looked at a lot of different software packages. And I really like this one, and so today what I'm going to do is I'm going to share with you guys some of the ways that I'm using Sizeware in resource plays or unconventional reservoirs in the Eagle Ford, but mostly in the Permian Basin. But I just want to give you guys a little bit of background. If you're not familiar with where Midland Permian Basin is, if you took a diagonal from Houston to Denver, from Fort Worth to El Paso, that's Midland. I think that's probably how I got its name. So with that, I'll give you guys a little bit of background of the wells that we're drilling out there. And I think one of the main things that I want you to take away today is that, you know, we're always, even on unconventional plays and drilling today, we still have a hard time of getting engineers to go ahead and spend money on seismic. And I think the way we need to sometimes reconfigure the argument or the discussion is say that in the Permian Basin, we're looking at between $25,000 and $50,000 per square mile to shoot seismic data. And at $85 oil, you're talking about 600 barrels per section. Can you get an uplift on your production of 600 barrels? And I challenge you to not find a way to increase it utilizing seismic data. And one way you can think about it is using mud loggers. We mud log every well, and the cost of that is about $10,000 to $15,000 per mud logger. That's $250,000. So by using seismic data and using these tools that we're going to talk about today, we believe that we can avoid geohazards and drill the best locations, and that is really priceless. The Permian Basin, Midland, Texas is situated right here. We own over 250 sections of land. We're one of the largest landowners in the country, Fasken is. I'm sorry, go back real quickly. This shows the wells that have been drilled into Wolfberry before 2000. There's been over 14,000 wells drilled in the Permian Basin, and if you know the Permian, it's really broken up into 3 different plays. You got the Midland Basin, the Delaware Basin, and the Northwest Shelf of New Mexico. So 14,000 wells were drilled prior to 2000. And then a snapshot many years later that last year, or between 2011 and probably February of 2013, over 13 wells have been drilled or permitted in that 2-year period, and over 38,000 wells have been drilled in just the Midland Basin, and over 1,100 horizontal wells. If you didn't know this already, we have seen a shift in the technologies, of course, but it was back in 2009 that horizontal wells in the red have overtaken drilling vertical wells. The majority of the wells that Fasken drills are vertical, and what we'll do is the Wolfberry, and we'll show this in the next slide. This is the representation of our activity. The yellow represents our ranch. We'll show you a seismic cut here in a second, but this shows some of the horizontal activity surrounding us. Have been over 35 wells that have been drilled horizontally in this area. It's a newer technology looking into Wolfberry. Next slide, please. And we've identified over 12 different zones that people have or are going to drill horizontal wells in it. And we're going to look at one of these zones today for the carbonate, that where it is present, we have better production. Next. This is a time slice of data over our ranch, and I have contoured this up when I make a depth map. This is consists of over 560 square miles of 3D seismic data. We're going to break this data, though, into smaller portions today for this exercise. Okay. What I typically do, and this was the last slide of my PowerPoint before we go to a we're going to be running a live demo, which yesterday was the first time I ever did that, and Summer Brown is going to be driving, and she's a great driver, so I've never really done this previously, doing a live demo. But I would like to show you this. This up here is our conventional, in this case, bandwidth extended seismic data. This one over here is an inversion that we have run. This is a pulse stack inversion, and I typically have 3 screens running, a map on one side, and then 2 different seismic viewers that consist of the inversion data and then the conventional seismic data. But in this case, on the regular conventional data, you really don't see anything, but with the inversion, you see a channel. And this is represented in this channel right here of this detrital material that these wells are spaced 660 feet apart. And yet we go from 8 feet to 68 feet to 51 feet, just that quickly. And so by using this data and using these data in conjunction, we're able to come up and determine different lithologies. Okay? So with that, we're going to go ahead and break up into two parts. The northern part is going to be a stratigraphic play where we're looking for the Dean line carbonate. We're going to look on the southern part will be a structural play using some of the coherency slices and some of the technologies that is in Sizeware that they have their own different calculations, but they also have rock solid image software for some of the attributes that are available. So the first thing we're going to do is we're going to go ahead and start running, we have created a coherency volume, and we're going to go ahead and start running time slices on that, and we're going to go use that to pick the faults. So after we start that, over there on the left, we're going to go here to the right, and what you see posted, or if you can't see it, and posted in the red is our isopac values of the Dean line. And I want to give you a little bit of information right now. When we did our log normalization, because most of our logs in this area are cased hole, we normalized over this entire area from about 4,000 feet a section. So we're going to have a little discrepancy at the end, but that is probably in the log normalization. But what we're going to do is we're going to go ahead and look at different attributes. So the first thing we're going to do is create a synthetic. So very easily we select an inline, and we're going to go ahead and then create a wavelet from our seismic data, extract that wavelet, and then we're going to apply that data, that wavelet, to our reflection coefficients. Now, what you see here in the yellow represents wells that have velocity functions already applied to them. When you bring your data, and one of the things that I really love about Sizeware is the ability to bring data from other modules. So we use Petra for our log database, and as my geologist is constantly changing his tops and I'm changing my depth maps, it's basically two buttons that I have to hit to import that data into Sizeware, which, you know, is seamless. And it's the same thing as far as exporting out those grids into Petra that can be used. So anyway, when you bring that data in, you go ahead and apply a velocity function, or as we stretch and squeeze this log on our left over there, we're going to come up with a velocity function. Do you want me to be on the other side somewhere, or am I okay here? You're great. Okay, so we come up with a velocity function, and then we can apply that velocity function to the other wells nearby, so that all those well tops now are, you can see them on your seismic line as you're moving back and forth. So just that easily we've applied that velocity function. So the next thing that we're going to do is we've looked at the data. We're going to go ahead now and flip from our conventional data over to our inversion data set. Because what we saw, oh wait, I'm sorry, we're going to do a synthetic model first. That's right. So we're going to select 3 wells that have sonic logs, and we're going to go ahead and have that synthetic cross-section utilizing the wavelet that we've extracted from the data set. And we have previously saved a template that shows the geology of the sands and the carbonates. Our target is the Dean line right over here. And we go from having a well that has 120 feet of Dean line over to the west, or to the east, for a well that has 35 feet of carbonate. We go ahead then and generate our model. And then we're able to overlay and be able to change the opacity of our seismic model and compare it to our seismic data. And as Summer is moving it over here, one of the things that you see here in the model is that that carbonate peak trough combination is stronger in that deeper well, and it decreases in the wells that have less carbonate. So we've looked at lots of different parameters, both on the inversion data and on the conventional data. So what we're going to do next is we're going to run one of the attributes, a zone attribute over this interval between the basal San Andreas, between the Dean line and the Wolfcamp. And what I found in this case is that using the pick on the Dean line, coming down, and then coming off the Wolfcamp, come up 12 milliseconds, that seems to have a very good correlation with the logs. So, as you can see here, here's the Dean line, here's the Wolfcamp, so we're coming down off the Dean line, up off the Wolfcamp, okay? So, you can look at a model and say, well, that looks really good, but until you do a cross-plot analysis, that's the only way to see if there is a relationship between those two parameters. So we're able to then go ahead and select all the wells, or we're going to grid it first here. So here's a gridded map on that attribute. And what we're going to see is that the wells that have the thicker carbonate have the larger zone of higher impedance. They have faster impedance velocities. And you can see that there, and those colors are in yellow. So then we're going to select our wells and place them in a cross plot. And we see that the relationship between the carbonate thickness and this seismic attribute is 0.78. Not bad for a first correlation. So what we're going to do now is take that equation, apply it to our seismic data to come up with an isopac value for that carbonate. And again, we're seeing that wells that have more than 70 feet of Dean line carbonate make better wells. So as we run that, and we're going to go ahead and post those values, you can see the variation in some cases is only a foot or two difference. In other cases, it's a little bit more than that. But again, I think that's because of the normalization that we did. But now, when we talk to the engineers, we say, look, if we're going to drill these wells first, and a lot of people purchase and flip data in the Permian Basin as far as properties, you're going to want to drill these properties first because these are going to give you your best bang for your buck. So in this case, we're using this tool to high grade our drilling locations for stratigraphic prospects. Okay? So now we're going to move down there to the south where we have lots of well control, and we're going to create a structure map on the Strong. But the first thing we're going to do, we've gone ahead and picked our surfaces, but we know that there are faults in the Strong. And so we're going to, instead of going through here right now and picking all these inlines and cross lines, which we will do for more detailed interpretation later, we can very quickly come over here and look at our similarity slice and identify faults. We're going to go ahead then and draw a polygon representing where that fault is, and then use that in our gridding when we go to our depth map. So you can see over here, we see a discontinuity right through here. And so we're going to go ahead and, draw a fault polygon around it. See it really well right there. And again, it's the rock solid images, different attributes that they have. I mean, they have a whole suite of them, and you can spin them off real quickly. I mean, talk about in a matter of seconds. Cut those time slices, take a look at them. If you don't like them, throw them away. So Summer has drawn that polygon. We go ahead and save it. And we're going to go ahead and apply that to our data set. Now, when I do structure maps, I like to create structure maps in several different methods. Sometimes I'll go down from the surface on down. Sometimes I'll go ahead and use multiple formations. And one of the things that we're talking with the size we're trying to improve is to be able to bring in maybe your RMS velocities or stacking velocities to help interpolate from where you have the well control, so you have some velocity variation. And that's one of the things they're looking at. So we're going to go ahead and just draw a seismic line on our base map here, just to show you that there really is a fault right there. Go back to the coherence, or to the conventional data set, and you can see that we have a nice fault there that cuts through the Strong right through there. And so We're going to go ahead now, and we'll go ahead and contour. We're going to do the basal St. Andrews, which is about 7,200 feet. We have a little bit more well control in that formation. We're going to use that to dam down to the Strawn. And while that's running, you want to open up that other PowerPoint real quickly? Show you an example of the Eagleford, and as that's running, it'll just take a second. Our first two wells that we drilled in the Eagleford were at the edge of seismic surveys, and I think geophysicists love to say two things. So we need more data, and we need to reprocess. And this is a case where we drilled this well at the very end. It's still doing over 4.5 million a day after 2 years. Next slide. In this case, we had some seismic data. We only had one well control on 35 square miles. We hadn't drilled very many wells out here. We still haven't drilled very many wells. So we used one well, and at the end of the seismic survey, we came down into the Buddha line. So we wasted time drilling, and we wasted an opportunity for another zone to frack. So if we had a little bit more data, we're able to vary our velocity across that area by using either interval velocities or maybe the inversion velocities, which gave us a little better depth structure, and we've been able to stay in the best part of the reservoir. Last week in Midland, the SPE had a society day meeting, and they came to the conclusion that, one of the speakers said that they need to do a better job of staying in formation. A lot of engineers say, you know, we can just take one zone, do a frac, and we'll get everything. Fracks will go up and go down. And what they're seeing is that's not really true. I mean, it's true, but you can do a better job of completion by staying in the zone. Okay, next one. And then this just shows a map where I have two different sets of contours. Oh, no, I'm sorry, this is Poisson's ratio, one of the different data volumes I brought into the data set. And this is an example where I've created that structure map using two different methods, and I like to go ahead and compare those maps and see if there's if there's any variation. In this area, the Eagleford, the apparent velocities are pretty stable. Okay. We applied microseismic to the data set. We're able to bring that information in. Next. Next. And we then use this microseismic information to help design our well paths. Next. And then we use we have a plan of where our planned horizontal path would be, and then compare that to our seismic. And then here's a well plan, and then next one is the final one where we go back as we're drilling the well to make sure that our well stayed in zone, and we had a very good well. This well has been on for 6 months. It's doing over 500 barrels a day, and I think 4.5 million a day. So it's a really good Eagleford well. Going back to our map now, we've gone ahead and run the structure. We have a depth map. We'll go ahead and apply our contours, and we'll zoom in around the fault area. You can see that even though we just drew that fault polygon, the depthing has honored the data for your gridding and also your contouring. Now we're going to go ahead and design a horizontal path. There's multiple ways to design a horizontal path. What we're going to do in this case, because we have a depth volume, is we're going to go onto the depth volume and draw our horizontal path on a zone that's 100 feet above the Strawn. We can also take this grid here and say, go 100 feet above the Strawn, and then that would also plot out a plan. We will take this plan then, give it to our drilling engineer, and then they'll use that when they design their drill program. So you see that we've drawn that out. We then are going to go over to our visualization. On our visualization now, we see our seismic data. That represented grid is our strong structure map. We see our well path. The well on the left is a well that has microseismic data, that we've been able to bring that microseismic data into it, showing the frac perforations and the resulting points, frac points. So, in conclusion, I'd like to thank you guys for your attention today. It's a powerful tool. I'd like to thank Fasken Oil and Ranch for allowing me to speak, and Sizeware for inviting me down here, and Summer for a great job of driving. And there's people here that they're dressed in orange. And if you have any questions, feel free to ask them, and thank you for your attention today. Have a great convention.